2,000 kilometers. This is the total distance covered by the railway network, cutting through the heart of the Taklamakan Desert. Why attempt to build a permanent structure across billions of tons of shifting dunes in one of the most hostile environments on the planet? It would seem that the constant movement of sand and the extreme heat would make any such foundation impossible to maintain. But without this infrastructure, the remote oasis cities of the region would remain isolated from the global supply chain, disconnected by an impassable sea of sand. Engineering teams faced the task of anchoring steel rails onto a terrain that is essentially a living, moving landscape. One can notice how the wind relentlessly reshapes the dunes, creating a surface that lacks any natural stability for heavy transport. But this is just the beginning. 12,000 workers were mobilized to confront these environmental challenges over the course of an entire decade. The project required the investment of more than $3.5 billion to transform a vision into a physical reality. It is visible how the tracks now slice through the vast expanses of the desert, where previously only sand and wind existed. At first glance, laying tracks appears to be a straightforward mechanical process, but in reality, every meter requires a calculated defense against the encroaching desert. Everything only gets more complicated when considering the sheer scale of the materials involved in the construction. The rails must withstand not only the weight of the trains, but also the thermal expansion caused by the scorching heat of the sun. The process is only gaining momentum as the network continues to facilitate movement across the region. One can notice the precision with which the sleepers are placed, ensuring that the heavy steel remains level despite the unstable ground beneath it. The camera glides along the straight lines of the path, showing the contrast between the rigid metal and the soft flowing textures of the surrounding dunes. Over $3.5 billion were utilized to ensure that the infrastructure could survive the abrasive force of sandstorms. Transition to the next level. Because the Taklamakan Desert is known for its shifting nature, the builders had to implement specialized engineering solutions to prevent the tracks from being buried within hours of completion. This effort represents a significant push of industrial capabilities to their absolute limits. The equipment gradually moved across the desert floor, leaving behind a permanent mark of human determination. Therefore, the completed railway now serves as a vital link, bridging distances that were once considered insurmountable by traditional means. The project does not end at this stage, as the maintenance of such a vast network in a desert requires constant vigilance and technical expertise. The molten heat of the afternoon sun tests the integrity of the steel daily. From here, the transformation of regional logistics moves into a new phase of operational reality. 2,685 kilometers is the total length of the Taklamakan Desert Loop, a massive circular infrastructure system that now rings one of the most inhospitable regions on the planet. Why did engineers decide to build a railway across a landscape that was long considered a blank zone on the national map? For decades, the northwestern frontier of China, stretching across the Xinjiang region and the vast Tarim Basin, remained entirely isolated from the rest of the country. This territory is divided by two towering mountain ranges and a desert expanse covering more than 127,000 square miles. But this is just the beginning of the challenges. At first glance, the desert seems empty, but in reality, it is a geological furnace and icebox combined. During the peak of summer, the ground temperatures can soar above 160 degrees Fahrenheit, creating a heat haze that obscures the horizon. Conversely, when winter arrives, the mercury plunges to -13 degrees, turning the sand into a frigid, abrasive waste. There is no existing power infrastructure to draw from and no natural water sources to support human life or heavy machinery. Beneath every step of a surveyor lies only constantly shifting sand, which provides absolutely no stable foundation for heavy steel rails or concrete sleepers. It only looks obvious to avoid such a place, but beneath this hostile ocean of dunes rests a massive concentration of untapped industrial wealth. Estimates suggest there are billions of tons of oil, coal, and most critically, rare earth elements buried deep within the earth. These materials are widely regarded as essential components for modern technological dominance. To access these strategic reserves, the state faced a stark reality that left no room for hesitation. There was no alternative but to attempt what was once considered a physical impossibility, constructing a railway directly across the desert. This necessity led to the creation of the Hutan-Rukyong Railway, an 890-kilometer line that forms a critical segment of the larger Taklamakan Desert Loop. Completed in June 2022, the project now stands as the longest railway ever built through a desert environment. One can notice how the equipment gradually begins to reshape the geography of the dunes. As a primary step in the process, hundreds of industrial bulldozers were deployed simultaneously to level the treacherous sandy surface. These machines cut down high ridges and redistributed millions of cubic meters of sand into lower depressions to create a stable construction site in the middle of the desert. The process is only gaining momentum. The camera glides along the leveled path where the foundation for the future tracks begins to take shape amidst the dust. The heavy blades rotate ceaselessly as they flatten the path for the heavy transport of materials. This initial leveling phase establishes the narrow corridor through which the thousands of tons of steel and concrete will eventually pass. From here, the transformation moves to the next phase of processing as the foundation is prepared for its permanent reinforcement. 1,200 tons of pressure from heavy machinery require a perfectly balanced surface to prevent catastrophic collapse during construction. Why is the stabilization of shifting desert dunes so critical for the structural integrity of the site? To the casual observer, leveling sand appears to be a simple act of movement, but in reality, any variation in density would cause the foundation to fail under the weight of a crane. Therefore, automated conveyor systems continuously push excess material away from the primary work zone, while surveyors monitor every inch of elevation. One can notice how the equipment gradually shapes the landscape into a uniform plane across miles of open desert. But this is just the beginning. Bulldozers scrape and level each section under strict supervision to ensure the slope remains within a fraction of an inch of the technical specifications. The process is only gaining momentum. Compactors then press the top layer to establish a firm and workable foundation for the next stage of development. Engineers discovered that injecting water into the loose surface serves as the primary binding agent for the individual grains. At first glance, spraying water on sand seems like a temporary measure, but in reality, it creates a denser and more cohesive structural layer. Using long sprinkler arms and intricate underground pipes, the team sprays controlled volumes of groundwater across the entire site. It is visible how the moisture penetrates several inches deep into the parched earth to lock the particles together. The process does not end at this stage. Heavy rollers move across the damp sand to remove air pockets and finalize the compaction of the surface. The constant rumble of steel drums echoes across the desert as each pass turns shifting dunes into a rigid base. The equipment moves at a steady pace of 3 miles per hour to ensure maximum density is achieved before the moisture evaporates. By the time the desert sun dries the area, the sand has hardened sufficiently to support the immense weight of mixers, supply trucks, and heavy lifting equipment. One can notice the transformation of the terrain into a solid foundation built entirely from sand and water. Everything only gets more complicated. Workers begin spreading a secondary base layer of reddish soil directly over the stabilized sand. Dump trucks pour out massive loads of earth, which are immediately pushed into an even layer by the blades of waiting bulldozers. This specific material adds significant weight to the sand below, which prevents the foundation from shifting under the influence of extreme heat or mechanical vibration. It only looks obvious to layer soil on top, but in reality, this provides the necessary friction to hold the entire structure in place. Each section is evenly spread and compacted once more to form a dense and stable base for the initial stages of the project. The camera glides along the reinforced surface where the earth now lays in a perfectly flat, immovable sheet. This concludes the preparation of the ground, leaving the site ready for the arrival of structural materials. Thus, the foundation reaches the standard required for the next phase of the production chain without haste. 130 degrees Fahrenheit is the temperature difference that forced construction crews to adjust their entire work schedule in the desert. Why did the workers choose to erect the bridge pillars almost exclusively under the cover of darkness? At first glance, the desert floor appears to be a stable foundation for a railway, but in reality, the shifting loose sand offered no structural support, and the daytime heat coupled with violent sandstorms made precision engineering impossible. Construction only gained momentum when the wind eased at night, allowing for the stable installation of the massive foundations. Reinforced concrete pile drivers operated ceaselessly through the night to penetrate dozens of feet of unstable surface material. Steel casing pipes were driven deep into the earth until the drills reached the necessary resistance of compact soil or solid gravel layers. It is visible how the equipment maintains the integrity of each deep shaft using a specialized bentonite slurry. This liquid prevents the surrounding sand from collapsing inward before the concrete can be placed. But this is just the beginning. Concrete enters the boreholes through tremie pipes, rising steadily from the bottom toward the surface. This method is utilized because it effectively displaces the slurry and prevents the formation of internal air pockets that would weaken the structure. One can notice how the heavy steel reinforcement cages are lowered into the wet mixture with jewelry-like precision. Even a misalignment of a few millimeters could lead to a tilted pile or a total loss of structural stability under the weight of future trains. 11,000 bridge piers began to rise across the horizon once the underground piles were secured. These foundations essentially allow the railway to grow roots deep into the desert floor, anchoring it against the environment. The process is only gaining momentum as the shafts take their final shape above the sand. Each individual pier stands at a height ranging from 16 to 50 feet. Slip-form molds allow the shafts to be cast in a continuous upward movement. The camera glides along the rows of columns, which now resemble a vast concrete forest stretching into the distance. It is visible how the repetitive nature of the casting process creates a perfectly uniform sequence of supports across the landscape. Everything only gets more complicated as the project moves toward the upper spans. The concrete settles and cures in the cooler night air, reaching its designated strength before the sun rises. This phase concludes the essential stabilization of the crossing, opening the road to the placement of the bridge decks. The material is ready to move to the next processing phase without haste. 650%, exceeding 310 miles, of the Hotan-Rokyang Railway is constructed atop elevated viaducts. One can notice how galvanized steel and salt-resistant additives are integrated into the structure to withstand the corrosive climate of the desert. Why choose such short, uniform spans between the concrete piers? At first glance, the repetitive design seems simple, but in reality, it is a calculated engineering defense. This specific spacing allows wind to sweep freely beneath the bridge, carrying drifting sand away so it can never bury the line, while simultaneously minimizing the structural effects of extreme temperature shifts. The process is only gaining momentum. Heavy crawler cranes or self-launching gantries lift thousands of pre-stressed concrete box girders onto the pier caps. Each individual girder measures over 100 feet in length and possesses a weight of several hundred tons. Specialized flatbed railcars transport these massive components across the desert terrain. One by one, the girders rise through the air with the slow, controlled tension of hydraulic cables. Engineers align the girders using laser precision to keep tolerances within just a few millimeters. This ensures the structural integrity of the entire skeleton of steel and concrete. It gets more complex further on. Once the spans are secured, crews poured the bridge deck slabs or installed precast concrete panels to form a smooth surface for the tracks. One can notice the pillars stretching toward the horizon like a silver ribbon cutting across an ocean of gold. Dust slowly settles as the sun sets behind the Kunlun Mountains, yet the work does not end at this stage. Next, concrete blocks known as sleepers or railroad ties are positioned along the track bed. These components hold the steel rails in their exact position and distribute the immense weight of passing trains across the foundation. Workers align each sleeper precisely to ensure the stability of the future line. It is visible how a lifting frame lowers the heavy steel rails onto the ties with methodical accuracy. Once the rails are fixed and fastened, the assembly can be utilized as a trailer for moving further materials. The molten stream of logistics moves forward as the transformation of the landscape reaches its final functional stage. 260 feet is the minimum length of each individual steel rail segment lifted during the final assembly phase. Why must these massive components be handled with such extreme technical caution? It seems simple to lay steel on a concrete foundation, but in reality, the slightest misalignment would cause the entire system to fail under the intense thermal expansion of the desert. Specialized heavy lift cranes maneuver the rails into their designated positions, where teams of technicians align them precisely along the established centerline of the track. The process is only gaining momentum. Workers manually adjust every joint and gap, to create a calculated tolerance for the metal to expand as temperatures fluctuate. One can notice how the fastening clips are tightened until they lock the rails permanently onto the concrete sleepers. This securing process prevents any bending or shifting of the infrastructure when subjected to the weight of heavy freight loads. It is a mandatory requirement before any locomotive is permitted to traverse the dunes. 11 months of continuous labor were required to finalize the hundreds of miles of track stretching across the arid landscape. The equipment gradually moved forward until the final bridge span was successfully installed. But this is just the beginning. Once the physical structure reached completion, the entire line transitioned into a comprehensive testing phase. Engineering trains equipped with high-precision sensors began traveling the route to gather data on vibration, rail temperature, and wind-induced sway. One can notice the heavy locomotives, weighing several thousand tons, crossing the viaducts to perform static and dynamic load tests. At first glance, the bridges appear immovable, but in reality, engineers must measure settlement down to the smallest fraction. The results confirm the success of the structural design. Elevation deviations remained within a margin of only a few millimeters, even after hundreds of consecutive test runs were executed. Because of the elevated height of the viaducts and the constant natural airflow passing beneath them, sand does not accumulate on the track surface. It is visible how the wind clears the path naturally. Everything only gets more complicated as the digital monitoring systems are activated. All operational parameters flow continuously to the central command post via a network of Internet of Things sensors. Solar-powered cameras provide a live feed of every section, allowing for real-time observation of the infrastructure. Transition to the next level. 6 months of rigorous technical evaluations preceded the official opening of the Hotan-Rokyong Railway in June of 2022. This final milestone completed the 1,685-mile loop that fully circles the Taklamakan Desert. The material is ready to move to the next processing phase without haste. 350 kilometers per hour is the threshold velocity maintained by Chinese trains gliding across a continuous concrete foundation. Why has China abandoned the traditional crushed stone ballast that still characterizes most railway lines in the United States? The answer lies in the transition from flexible, loose material to a unified, rigid body. In North American infrastructure, thick layers of crushed stone are laid beneath each rail to distribute the weight of the locomotive. This material only looks obvious in its simplicity, but in reality, it performs 3 critical functions simultaneously. It distributes the massive tonnage of the train, maintains the stability of the track structure, and ensures that rainwater drains away from the track bed. But this is just the beginning. The process is only gaining momentum as China pursues a completely different engineering path for its next-generation high-speed networks. One can notice how the traditional stone layer is entirely replaced by slab track, a continuous concrete foundation of immense durability. It is visible how the rails are fixed directly onto the flat concrete surface rather than being nestled into gravel. This entire structure becomes one unified body that is stronger and more incredibly precise than any stone-based system. Precision is managed by laser alignment systems, while fully automated machinery handles the installation of the steel. Everything only gets more complicated when considering the speed requirements. 350 kilometers per hour is achieved because the concrete eliminates the shifting inherent in loose stones. Construction begins with the preparation of the subgrade. This involves the grading and compacting of multiple layers consisting of soil and gravel until a firm foundation is established. The depth of this compacted base typically ranges from 2 to 4 feet, depending on the specific terrain and the expected loads from passing trains. At first glance, the preparation seems simple, but it requires absolute structural integrity before the next layer is added. Transition to the next level. Engineers begin spreading the ballast once the base has been stabilized. Unlike the Chinese slab track, this layer is not bonded together by any chemical agent. It remains loose so that it can absorb the constant vibrations of the passing cars and allow rainwater to drain freely from the surface. The equipment gradually levels the stone to ensure the thickness remains consistent across the entire length of the line. One can notice how the jagged edges of the crushed rock interlock to provide a friction-based stability that holds the wooden or concrete sleepers in place. This concludes the primary preparation of the foundation, allowing the project to move toward the final alignment of the rails.